right. So when we think about the word electronegativity, what was the definition that we had before? You guys, please put your phones away and let's take notes, okay? What was the definition of electronegativity? We said that electronegativity is how much atoms want or can attract or can take in those electrons. Okay? And that was kind of the chemistry according to Candace's version, but how much atoms want electrons. So we also talked about a trend on the periodic table. Okay, so we'll draw. Get ready. Here's my lame-o periodic table drawing. We'll draw our periodic table. Okay. And we'll label it because that does not really look like the periodic table, but we know what it is. What is the trend for electronegativity? Show me on your finger or point to the way that it goes up. How does it increase? Right. It goes up and to the right. So this trend increases as it goes up and to the right. What is the most electronegative element? Because we're not really going to look at the noble gases. They're already satisfied. So think about your periodic table. Pull that out. What is the element that is highest and to the right? It's a noble gas there, right? So it's satisfied. Helium's not highest to the right that needs something. So we're going to go fluorine is the most electronegative. And we'll just kind of make a note of that right here. Okay. All right, so that's kind of reviewing electronegativity. How much is that atom going to really draw in electrons? Okay. But what about polarity? What do we know about polarity? The Earth has poles, right? And the Earth has a North Pole and a South Pole. What else has poles that you know about? Aren't there North and South poles on magnets? Now let's think. The Earth has a North and South Pole because of its magnetic field. Magnets clearly have a magnetic field because of electrons. What else has poles? You might not know this, but batteries have poles. Have you ever put batteries in and you put them in backwards? Did they work when you put them in backwards? No, it's frustrating. You got to take them out and do it all over again. So, batteries. Why do you think they call them a plus and a minus end on batteries? One's positive and one's negative. Those electrons in the electricity go towards the positive end and they run away from the negative end. So it has something to do with electrons. We're going to try this polarity business. So if we're talking about covalent bonds and they're supposed to share electrons, how might we get a positive and a negative end on our compounds? We'll think about that. Okay. So let's kind of take a little very direct note for a second. Covalent bonds share electrons. Have you ever tried to share something with somebody? Is it ever equal? I mean, like, think about, I guess before COVID, you might have shared an and ice cream with somebody. They're going to take bigger bites, right? It's not equal. So, or sharing like a sweatshirt with somebody. You guys go to the mall, buy something expensive, and you say, oh, we'll share it. They're probably going to have it 3 weeks out of the month, and you're going to get it 1 week out of the month. Still sharing, not equal. So sometimes when things are shared, it's not equal. So not always equal. That's the same for atoms. Okay. So if atoms share nicely, and what are they sharing again? Electrons. If atoms share their electrons equally, so if they share the way sharing was intended, it is a non-polar bond. So the electrons are spread out evenly. Okay. But we know that's not always the case. We can't even share evenly and we have a conscious thought about it. But if atoms do not share equally, what's the other option? We're going to call that a polar bond. Okay? And so electrons stay at one atom more. And this is due to electronegativity. Okay? So if we come back and put these two ideas together, come back to our periodic table. The atoms that are up here high and to the right are going to tug those electrons harder and keep them. They want them more than the atoms that are lower and to the left. Okay, so keep that conceptually in your mind, and then let's talk about numbers, because there's always numbers involved in this chemistry business. Okay, and that's where we're going to kind of come back to the lesson too and look at, we have this electronegativity values that you're going to be revisiting and bringing those values into what we're doing. So let's kind of look at it. See francium, 0.7. We look over oxygen, higher and to the right, 3.5. Makes sense, right? This is clearly making sense to what we already know. All right, so let's take some notes and we'll go back and look one more thing on the lesson. You can see a very pretty picture. We're going to draw that in our notebook in just a little bit. But I wanted to see that there is a pretty picture if you would like to look at that in the screen as we take our notes. Okay. So what we're talking about is actually the polarity of the bond. So let's label it as such. Bond polarity, or the amount of sharing. Okay. So when we put it in that perspective, we could kind of have two ends. This is a spectrum. We're going to get an equal share down here. Sharing equally. Okay. Sharing equally is on one side of our range. Not sharing is on the other. Okay. And then there's clearly a range. There's clearly space in between. So what did we call up here? Sharing equally was nonpolar. So let's put our label on our range. And then we'll add some numbers. Nonpolar. Polar's somewhere in the middle here. And these are both covalent bonds. Can atoms bond and not share the electrons? Yeah, It's called ionic bonding. Because remember, those electrons are stolen in ionic bonding. They're stolen. Now, that is pretty qualitative on there. There's no numbers. So how do we figure this out? The difference in electronegativity. So that's where we're going to go back to. We're going to go back to those numbers on that periodic table and find the difference. So if we have a 0 difference, we're in the nonpolar range. Once we get up to a difference of 0.4, then we enter into the polar range. And that's going to go all the way up until 2.0. And the biggest difference you can have is 4.0. Okay. So I want you to think about this kind of like a number line. Okay. Obviously, 0 is the least difference you can have. They're the same number. 0.4. And then we're going to get to the polar range. 2.0, we're not polar anymore. We've made a shift. We're on an ionic bond. Okay. So everything between 0.4 and 2.0 is polar. I'm going to make it blue because it's got to be cold, right? If it's polar. No, just kidding. So I want you to think about this like a number line. If we are between 0 and 0.4, we're nonpolar. If we're between 0.4 and 2, then we're polar covalent. And if we're after 2, then it's an ionic bond. Give me a thumbs up if that makes sense. Good. Okay. All right, so let's do an example. All right. I'll do a couple of examples. Let's go with carbon monoxide, just one bond. All right. We'll think about the element. We know that this is a thing, CO. So we have carbon that has 4 valence electrons. We have oxygen that has 6 valence electrons. And then we're looking at it going, well, these are lonely, so they'll make a bond. These are lonely, so they'll make a bond. Well, in covalent bonds, remember the electrons are all shared. So these valence electrons could find their way anywhere around any of these atoms. And that's actually what happens. This electron decides to go be buddies. They're breaking rules here. And then these electrons, these shared pairs, they decide to come in between and be shared with both of them. So we actually get this situation. It's a very linear molecule. It's only 2 things. Of course, it's a straight line. But then, all right. So now we've looked at the formula. We've looked at how it's laid out in a Lewis structure. What about this electronegativity business? Well, we have carbon and we have oxygen. So we're going to come back to our scale, our numbers here. Carbon is 2.5 and oxygen is 3.5. So we're going to write those down. So we need to find a difference. I'm not going to have negative numbers in this. We just need the absolute value difference. So we're going to say 3.5 minus 2.5 is 1.0. All right. So where does 1.0 fall in this number line? It's bigger than 0.4 and it's smaller than 2.0. So we have a polar covalent bond. Okay. Now, just very quickly, what if I have CO2? we know that carbon would be the central atom, oxygen would be on either side. We've already done this molecule before. We know that we're going to have a double bond between, so we get this idea. Right? Well, we still just have carbon and oxygen. And we still just have carbon and oxygen. These elements still have the same electronegativities that we just did. So we only have to do that same problem. The difference between the oxygen's electronegativity and the carbon's electronegativity is still 1.0. So we're still going to have polar covalent, even though we have more than one bond. All right, thumbs up if that makes sense. Okay. All right, so what you're going to do for the lesson today, for you to turn in, if you scroll down past these exit questions here, right here, this part, you can copy this and paste it into your text entry box. So I'll show you that in just a second. Okay, so I brought us back into student view. What you can do if you go up to submit the assignment, hit submit assignment, you're going to pick text entry. And then we're going to come up and just copy this, go from practice to just the red letters there, Control C. And in your text entry box, you can hit Control V. It should do exactly that and give you the data table to work in. And so let's do a couple of them as examples so that we can make sure we understand what we're doing. Okay. So I'm looking at this and I say, well, what on earth? All right. I'm going to use my notebook because it's right next to where my notes are. And so I look at the first problem. It says oxygen and oxygen. So if I consider those elements, they both have 6 valence electrons. They're going to make just the lonely electrons connect. All right. But the electronegativity difference value. Well, oxygen is always oxygen is always oxygen. So if I scroll back up in the lesson, oxygen is 3.5. I'm going to say 3.5 minus 3.5. Well, that's almost a silly math problem. That's 0. So in my answer, where it says electronegativity difference value, I'm going to type 0. And then it says bond type. Well, if I look at my notes that I had, my picture here, if my 0, that's nonpolar and it's covalent. So in my answer, I'm going to write nonpolar covalent. And then I look back at what I had written for that example, and I know that my oxygen is going to be, I just need 2 of them. So my formula would be O2. And my formula for the bond, I'm going to put O, and then I can use the subscript tool here and make it a 2. Okay, give me a thumbs up if that makes sense and that seems like something we can do. I see no thumbs. Okay, all right. And then just go down and answer the questions, and you're going to hit submit on that. I think that's it.